Okay. Happy New Year. So we are now entering the last third of the Statistics for Data Science course. And we finished before Christmas with non-parametric inference, which was kind of the last thing about frequentist inference. And we're starting today with Bayesian inference then. As already pointed out, there used to be a session on prior distributions, which was about, or was supposed to be about the selection of formal rules. What?
Die FO-Evaluation. So jetzt in den nächsten 2 Wochen.
Ja, ich mache das normalerweise zusammen mit der Prüfung, damit wir das auch sehen. Aber dann wieder. Danke. Wie ist jetzt in English? Good. So, start again. Last third, Bayesian inference. There used to be a session on prior distributions, so the construction of prior distributions based on formal rules. For now, I've taken it out of it mainly because I think this is something we will discuss in the Übung today. We have to see how many Übung sessions we still need, which I think is one more than we have time for, but we will check that later in the Übung. The other thing is that I also doing support vector machines next week in machine learning, and it just is getting a little bit too much. So this stuff we will do. Let's see what happens with the prior distributions. As for the exercises, I've expanded on the Bayesian inference questions. So there will be, because there weren't any questions about prior distribution so far, so now there will be more questions about Bayesian inference. I can also, if you really are interested in this prior distribution thing, it's based on a paper by Carsten Raftery. You can also do something about this if you like. It's just a little bit to prepare. So the main change here with respect to the prior distributions is due actually to the Übung, because I think we need more Übung sessions than we have time. So in Bayesian inference now, we will today discuss foundations and conjugate inference, which is kind of the analytical way to do Bayesian inference. Then next time we're going to discuss the very important topic of Bayesian filtering. So Kalman-Filter, Rauchtung, Striebel, Smoother. And then we're going to discuss numerical methods. This was, I think, initially called Markov chain Monte Carlo. This is still, if you want, Markov chain Monte Carlo, but it's more leading up to Markov chain Monte Carlo, because to understand what's going on with MC-MC, you need to have quite some background, and this is better called than numerical methods. And the last thing that we will discuss is variational inference, which is kind of the most general framing of inference in statistical models that I can think of, and that I've been also doing some stuff in, or trying to understand what's going on there. And one can actually show that a lot of these inference methods are special cases of variational inference. This is why it makes sense to discuss it. And of course, in modern machine learning, it's variational autoencoders, which is the new word for variational inference, which is already the new word for variational Bayes. Anyway, yeah, so Bayesian inference. That's what we're going to start with. Who in the undergraduate statistics did stuff on Bayesian inference? No one. I know that you guys know a little bit about Bayesian inference, of course, but yeah, it's a little bit strange that it still hasn't really entered the undergraduate curricula. Also in mathematics, it's interesting because mathematical statistics, at least in Europe, is really strong in the frequentist asymptotic framework, or at least in the continental European mathematical statistics. In US, Anglo-American statistics, there's more Bayesian inference. Yeah, so it's not really true that Bayesian inference is somehow more it's a little bit more novel, but it's not like it has not been developed like the last 20 years or something. So the big developments in Bayesian inference after the frequentist stuff in the early 20th century were then in the mid to late 20th century. So it's not really novel, and it's also not really in any way better or something. So, but I think it's an important aspect of statistical inference. And the interesting thing is that in machine learning, for some reason, Bayesian inference is, I think, even more prominent than it is in mathematical statistics. So kind of weird, but that's how it is. Yeah. So today, then first, some foundations about Bayesian inference and some examples for conjugate inference. This stuff that I'm presenting today is mainly out of my head and with some inspiration from these books, but also a little bit different from these books. So you find in any modern probabilistic modeling statistical textbook, you find some parts on Bayesian inference. I think the Held book tried to juxtaposition statistical inference in the classical framework and in the Bayesian framework, or let's say in the frequentist framework, in the Bayesian framework next to each other quite a lot. Wasserman is a little bit dominated by frequentist. There's a little bit of Bayesian inference also in the de Groot and Scherwisch, but not that much. Then you find introduction to Bayesian inference in many machine learning books, but the problem there is always that these are the machine learning books and the probabilistic details are a little bit lost. So, yeah. This is the outline. So first, foundations on the Bayesian paradigm, and a little bit on inference summaries, because just the posterior distribution is maybe not enough. And then two very common and basic models in Bayesian inference, the better binomial model and the univariate Gaussian model, to get a first feeling of what Bayesian inference entails and how that then looks. But these are, of course, only two examples. More models will be discussed in the Übung, and there are many more. Yeah, so let's just get started to have some content, if there are no questions for now about outline, things like that. Good. So already in the first lecture, when we discussed this overview, I introduced these central postulates of frequentists in Bayesian inference, which are from the Wasserman book, and I'm just bringing them up right now to think again what we are contrasting the Bayesian inference now with. So the frequentist inference, where probabilities are mostly interpreted as limiting relative frequencies and considered objective properties of the real world. So where probabilities are somewhat real, although they only really come into reality in the infinite limit. So then the question is how real they really are. But definitely probabilities are mainly used to describe frequencies and not so much to describe uncertainties. The parameters in frequentist inference being fixed and unknown constant, which are known as true but unknown values. And importantly, and this will be the big difference in Bayesian statistics now, in frequentist inference we never made probability statements about parameters. So there was never a probability distribution over some parameters, and there will be now. And here in frequentist inference, of course, what we've looked at in asymptotic statistics and in bias and so on was to study the sampling distributions of statistics and then make claims about optimality based on that. Now in Bayesian inference, the first kind of philosophical big difference is that the same probability distributions, the same probability densities, so again Gaussian distributions, beta distributions, Bernoulli distributions and so on, they are now not interpreted as limiting frequencies but as degrees of belief, subjective degrees of belief. So where basically relating to common language, where you can say things like the probability that it will rain this afternoon is 0.5, which you can already discuss whether this is now a statement of subjective belief. I mean, it's definitely subjective belief because if it's about only this afternoon, because this afternoon will only happen once, and it will happen today, and it definitely this afternoon, or the probability that Trump will become president again now that he fights a war. These things don't have limiting frequencies, but you can still talk about the probability of them, and these probabilities then are degrees of belief. The important thing is that the formal framework, the mathematical framework, remains unchanged. It's not that the Gaussian somehow now looks different, it's just what the interpretation is that changes. So that's kind of the more overarching philosophical, maybe even subtle thing that one needs to get used to, and then always question oneself once I have calculated some probabilities, what does that really mean? The more obvious change in Bayesian inference is that we now make statements about parameters. We make probabilistic statements about parameters. So the probability that the true but unknown value, for example, is in a certain interval. What you need to also be careful is that you don't misunderstand distributions over parameters, especially prior distributions, as things of the real world, like in hierarchical models. The idea is still that there's one true but unknown parameter value outside, that you then, on your side of doing data science, you have a probability distribution about the value of this parameter. But there's not a probability, so that's not the basic assumption that there's a probability distribution of parameters and they somehow get sampled in the real world or something. You can have these ideas also, but they relate more to hierarchical models than to basic Bayesian inference. Oops. Yeah, and based on these probabilistic statements about parameters, so that there are distributions about parameters, we can make further inferences, such as giving point estimates. So, for example, the maximum a posterior estimate, which we will see later, or intervals, which are then called credible intervals, which we will also see later. Yeah. Now. So this is these are the kind of big different frameworks. I think if I manage, we had this I made this nice figure about true but unknown values, point estimates, confidence intervals, and hypothesis testing in the other slides. I should make a figure like this for this as well. Then it maybe gets even clearer, but the important thing is now we have probability distributions over parameters. Now, let's get really to the point. So this is kind of the typical setting of Bayesian inference. And I tend to call Bayesian inference and Bayesian modeling, Bayesian statistics, I tend to call this probabilistic modeling because first of all, you don't go into these discussions that you're sometimes, if people have never heard about Bayes, the first thing they will say, yeah, but you have a prior. What about the prior? And if you don't come up with the name Bayes, then maybe they are not triggered to say that. The other thing, it emphasizes also that Bayesian inference is just working using probability theory. So I like to call these models that are then used to model the distributions of data and parameters, because we now give probabilities also to parameters. I like to call them probabilistic models. By a probabilistic model, I mean a joint distribution over a family of observable random variables x1 to n, so x1 to n. These are, of course, again, the random variables like in frequentist statistics that model the data and for which we assume that each data point is a realization. And this is the new thing, not directly observable random vector theta. So, for example, if these are all conditionally independent Gaussian random variables, then theta could be mu and sigma square. And this vector models parameters, and this now has an associated probability distribution. And the basic model behind any form of Bayesian inference is a joint distribution over the data random variables and the parameters. And these joint distributions are also referred to as generative models. This, I think, mainly comes from the Vapnik, as my current reading on support vector machines tells me, from the Vapnik discrimination between generative and what is it called? Predictive modeling. Any kind of model is generating data, but you find people use this term generative models a little bit more for these kind of models. For me, these are probabilistic models. It's a model over parameter values and over data. Now, often, and this is of course what you will have heard about Bayesian inference, these probabilistic models are specified in terms of a marginal PDF or PMF over the parameter, so P theta, and a conditional PDF or PMF of the data points, namely the distribution of the data conditional on a value of the parameter. So this is the typical specification, that you specify maybe first this conditional PDF, so the distribution of the data points given the parameter. Then you specify the marginal distribution of the parameter, and then if you multiply them, you have a joint distribution. If one goes really subtle into things, and, for example, bases the entire probabilistic framework based on conditional distribution and Markov kernels and so on, then one actually starts the whole thing more here and not here. But I think it's from first understanding the Bayesian mechanics, it's a lot easier to leave this idea of prior and posterior and to go to joint distributions over data and parameters that one defines by a marginal and a conditional distribution, and then evaluating the other marginal and conditional distributions of this joint. But you will also notice here that I start to use kind of machine learning probabilistic notation. So the nice so I still want to say, when I use the small p, that we are dealing with a PDF or a PMF, but I will hardly ever in the Bayesian inference scenario actually write out the probabilities per se, so our bold p, and CDFs will also not feature, so our large p will also not feature much. So this is something that you in some way need to get used to in machine learning. There, this P can mean many things. Usually it means PDF or PMF. Most of the time it actually means PDF. Sometimes it actually means distribution. Sometimes it means probability. So one has to relax there a little bit from the very precise mathematical nomenclature of probability theory. It makes things easier in terms of notation, things look nicer, but sometimes then if you really want to understand what's going on, you need to be a little bit more careful, specifically in examples where it's of course important whether you're dealing with a PDF or PMF or maybe neither. The nomenclature hence is then also that this marginal PMF and this conditional PDF are often then referred to as prior distribution, could also call it prior marginal, and the likelihood, which could also call it conditional probability density function. And another assumption that is often made, which is the same assumption as our IID assumption in classical statistics, is that the data are conditionally independent and identically distributed. So, and this conditionally independent and identically distributed now means that the conditional distribution here over all data points factors into a product of n conditional distributions over each individual data point, and these are usually assumed to be equal. For the first data point, for the second data points, it's the same, but it's a conditional distribution over over the data point and given the parameter value. Yeah, so the data points are not independent, unconditional anymore, because so far the parameter only used to be a parameter, but now that the parameter is a random variable, it's the conditional distributions of the data points that are independent and identically distributed. Yeah? And this basically generalizes the notion of IID data from the frequentist to the Bayesian case. Yeah. Then, if you have such a probabilistic model,
question.
Yeah.
On the last slide. So the last part, the last equation, pxy given theta is equal to. So they all have the same. This means this comes from the identically distributed. It just means they all follow the same. On the right side, the last equation.
This here?
No.
And this
yeah,
here?
Yeah.
Yeah. This is
just means identically distributed and following the same PDF.
Yeah.
Yeah.
Yeah. Yeah. That's what this is supposed to mean. So. Yeah, one has to think a little bit always about conditional independence versus non-conditional independence. Conditional independence means if you fix the value of the parameter, then these things are independent. That's what it means. Yeah? And this is just, this is just, I didn't know really how to write that they are all the same, so I wrote it like this. So they are equal to the first one. This is also sometimes not so often. These data points are in these introductions. There's just a big D, and this. Then the question is what this means. And usually it's a data set. And then if you want to do inference and so on, then you need to make sure that you differentiate the distribution or the conditional distribution of a data set from the distribution of each individual data point, which, depending on whether you assume conditional independence or not, can of course be different. The most interesting thing, of course, in Bayesian inference is the posterior distribution. And we, of course, introduced this not directly observable random vector theta. So not directly observable, that's somehow from our discussions. So of course, you, based on the data, you get some information about the parameter, but you don't directly observe it. To call it unobservable in the old days, and if you look into, for example, graphical models or Bayes nets, these random variables are also called unobservable. And yes, they are unobservable. You don't get real readouts from them, but you of course get some information about them based on the observed random variables, namely the data. So this is why I now call it not directly observable. It's maybe a little bit over subtle. You can also call it the unobservable random vector. Now, what you're of course interested in making statements about the probability distribution of this not directly observable random vector theta, given the observable random vector x, so the data, and this distribution, so this conditional distribution here, theta given x1 to n, is called the posterior distribution. And of course, you can evaluate the posterior distribution based on Bayes theorem, where you take the joint distribution and you divide by the probability of the marginal probability of the data. And here it's written in terms of the prior times the likelihood, and then integrating over the parameter the joint distribution, so that in the denominator you have the marginal. So this is just Bayes theorem. Of course, we discussed Bayes theorem in the beginning of the course. So Bayesian inference and Bayes theorem are not really the same thing. Of course, Bayes theorem is used here, but Bayesian inference, you can't do Bayesian inference without Bayes theorem, but you can do Bayes theorem without Bayesian inference if you want, because it's a question about interpretation. This is kind of the rule of thumb or something. To discuss the posterior distribution. The likelihood of the data given the parameter, or the conditional distribution of the data given the parameter is also referred to as likelihood. The marginal distribution of the parameter is called the prior distribution, and the marginal distribution of the data is called evidence. Often I will give a little bit of an idea why that is later on. So you can also write the posterior mnemonic as likelihood times prior divided by evidence, although these things don't really help. If you really want to do conjugate inference, then you really need to write out what's going on, and so it doesn't help that much if you know this and you think you know something about Bayesian inference. Well, do Bayesian inference for a specific model and think about what the likelihood, the prior, and the evidence are, and then you do Bayesian inference. One thing is that for a given data realization, so for a given x1 to n, this probability, this marginal probability, is a constant. This thing varies as a function of theta because it's a probability over theta. That means here in the numerator you have something that varies with theta, namely the marginal, and also the probability of a data set is a function of theta, but the numerator doesn't really vary. It's just a normalizing constant, and if you think more about it, what you actually have here is the joint distribution, and I hope it's clear from, I think we discussed joint distributions, that conditional distributions are essentially joint distributions but normalized so that they integrate to 1, and this integration constant is here in the denominator, and it's the probability of an observed data set, the marginal probability of an observed data set. So one can, and this is what one sometimes sees, and we will also use later, also express Bayes' theorem that as follows, that the posterior distribution is proportional to the product of prior and likelihood, which just says that the posterior distribution is proportional to the joint distribution, which is what I'm saying all the time, that the joint distribution is the important thing. This is sometimes helpful because the normalization constant ensures that this posterior distribution is a proper distribution. So for example, if you have a PDF, something like a PDF here, and you know from looking at it, okay, that looks like a normal, this looks like the kernel, so the thing where the action is of a normal distribution, then you know, okay, the normal distribution normalization constant is 1 over square root of 2 pi sigma square. So I can I find this normalization constant just by my general knowledge. This is this thing which makes Bayesian inference always a little bit it's not that recipe-like. This is what makes Bayesian inference, especially conjugate inference, always a little bit less accessible than, for example, maximum likelihood, where you have this recipe. In conjugate inference, it depends on the model, and then you do this, and it's a little bit less recipe-like. Unless you do variational inference, then it's very recipe-like again. Yeah, so that's the posterior distribution. One thing about posterior distribution that we will also, that basically contrasts what we are doing today when we think more about Bayesian inference from the statistics perspective, that we have n data points and we now want a statement about the parameter, to what we are doing next week, that data is basically continuously arriving. I think in modern language that's streaming data, internet, something, data, artificial intelligence. So batch Bayesian estimation refers to what we've just described. So you specify a prior distribution, you specify data likelihood, usually based on this conditional independence of the data points given the parameter, and then you use what we've just shown you. You use the entire data set. So here we've just written the joint distribution of the data point specifically as conditionally independent, and you use this for Bayesian estimation, and then you have a probability distribution over the parameter given n data points. So that was what we've already seen. I've just now called it batch estimation, batch Bayesian estimation. What you also often see is specifically if data is continuously arriving, and which leads to these things like today's posterior is tomorrow's prior. which also kind of relates to this Bayesian inference of accumulating knowledge and always updating things, is the following. You start with a prior distribution. You specify the data likelihood for a given data point. So this is essentially the same as previously, but now you update your parameter distribution one by one. So you first update based on the first data point. So you use Bayes' theorem for the joint distribution of p theta and x1 to do the posterior distribution. And then with this posterior distribution, the p theta given x1, you enter the update based on the second data point. Yeah? So you then look at the thing, and this is important here. Of course, your probabilistic model gets a little bit larger. So here you have the distribution of the joint distribution of theta, x1 and x2. Actually, you always outside this in the other one. Here, if you would now decompose this based on the definition of conditional distributions, you would of course also have px2 conditional on theta and x1, but then because, and this is then also included here, the data points are conditionally independent. Given theta, you can get the x1 out of this condition statement and end up with this, so that the joint distribution of x1, x2, and theta takes this form based on this definition. Then if you do that until n times, you end up, and this is the main point I want to make here, with the same result as in the batch case. Yeah? So you either use Bayes' theorem based on n data points and update your prior distribution, or you do it step by step. If you have the same, of course, if you have the same data points and the same number of data points, and you start with the same prior, either in a batch or recursive Bayesian estimation, you end up with the same posterior distribution. And this thing will be, when we talk about Bayesian filtering and Kalman filter next week, this will be the mode that is happening there, so that you do step-by-step updates. This is more the mode that you would do in a classical statistics setting, where you have obtained 20 data points, and based on these 20 data points, you now want to update your parameter distribution. This is then more the online learning. Good. Two more things about the Bayesian paradigm. So far we've seen the posterior distribution. Of course, you can also, based on the joint distribution, so based on the probabilistic model, you can also form the marginal distribution of the data. So by integrating out the parameter random variable from the joint distribution, or if you want from this expression of the joint distribution as the prior and the likelihood, this distribution of this marginal distribution is then usually referred to as marginal likelihood, as marginal data likelihood, or as model evidence. I like the term marginal data likelihood a little bit more than evidence, because it's a joint distribution. You have a marginal data distribution. So, and this is also where variational inference starts. With respect to model evidence, you can use this marginal probability of the data, or marginal probability density, or marginal probability mass of the data under a given model. Can use this as a basis for inference. It's I don't want. So it's somewhat related to likelihood ratios, but it's not really likelihood ratios, because you don't do optimization of parameters here. You integrate out the parameters. These marginal likelihoods, they if you have two models, so two probabilistic models, which are called P1 and P2 here, which have the same data outcome space, so they generate qualitatively the same data, but they might have different parameter spaces. So this is why I have a theta1 here and a theta2. And you look at, for one data set, you look at the marginal probability of the data under one model versus the marginal probability of the data under another model, and you contrast this. This ratio is known as Bayes factor. It's a basic model evidence criterion in Bayesian inference. If the probability of your data under model 1 is high and the probability of your data under model 2 is low, then you would say there's more evidence for model 1. Note that here the posterior distribution doesn't play a role, yeah? It's actually, there's much more, so this is the only slide I have on that, but to get to an interpretation why this is a good model selection criteria and which other model selection criteria might be advisable and so on, one would have to develop things a little bit more. Here, just for this first introduction to Bayesian inference, we are happy with saying, okay, it's the marginal likelihood of the data, it's the probability of the data set under probabilistic model. If this is large, then the model can explain the data well. If this is small, then the data might not explain the model very well. It's also sometimes called the prior predictive distribution, and prior because here the integration is with respect to the marginal distribution of the parameters, so the prior. And of course, you can say, yeah, but now I have some information about the parameter, shouldn't I factor that into my model comparison? And yes, then you can do other things. Bayes factor works like this. That's the point here. Finally, the posterior predictive distribution. If you have a joint distribution and you have a posterior distribution, you can of course ask what is the distribution of yet another data point given this posterior. And this then would look like this. So the conditional distribution of data point n plus 1 given n data points is, of course, based on the definitions of conditional probability, given as the integral over the posterior distribution times the data likelihood. And of course, usually we would assume that the distribution of the n plus 1 data point given theta is the same as it was for all of them before, if you don't have any reason to believe otherwise. And then you can, based on your posterior distribution, make predictions about new data points. And this is referred to as posterior predictive distribution. And if you want, this factors in the uncertainty over theta. So of course you can always kind of make predictions about data based on plugins of the parameters. So for example, you do maximum likelihood estimation, then you can plug in your maximum likelihood estimates into your model and talk about the distribution of additional data points on the model given these maximum likelihood estimates. With maximum likelihood estimates, you would typically neglect any uncertainty, and here you would factor them in because you put them in. So the main points here in this first session were that, to go over that again, that in Bayesian inference you always start with a probabilistic model. You have a joint distribution over parameters and data points. And then you can look at different marginal and conditional distributions of this joint distribution. So if you only look at the marginal of the parameter, you call this prior. If you look at the conditional of the data given the parameter, you call this likelihood. If you look at the conditional of the parameter given the data, you call that posterior. If you look at the marginal of the data, which we have here, you call this modal evidence. And if you want to also make predictions based on the observations that you already made, you call this posterior predictive distribution. I think one of the reasons I include posterior predictive distributions here, because sometimes Bayesian inference and machine learning, predictive modeling are contrasted, but of course you can, with every model, you can make predictions, and so posterior predictive distributions and cross-validation predictions are kind of the closest things, but of course Bayesian uses the entire data available and not leaves some out for data for testing and so on. But that's a different story. But so I just wanted to stress that predictive modeling also happens under the Bayesian paradigm. Good. Yeah. Then I think actually this is a good time for a break before we go into inference summaries. Other questions from about the Bayesian paradigm as I presented it here?
How do you choose the first prior distribution?
Yeah, so this is this session prior distributions. So there are basically two kinds of philosophies or two kinds of approaches to that. One approach, which is more the subjective Bayesian, says you should in some way cast your knowledge into a probability distribution, and then you need to find a way how to do that. And Lindley, so Dennis Lindley, a very famous Bayesian statistician, they thought long and hard about it, how you would do that. Of course, if you are more pragmatic, so for example, if you have a model and you want to do Bayesian inference on that, and you think about some parameters that are known, you can give them very tight priors and they don't change, and then you have encoded known parameters in your model in a Bayesian setting. But in principle, you should somehow have good reasons to bring up these kind of priors. That's subjective Bayesianism. Then you have objective Bayesianism, which tried forever to find uninformative priors. So the first thing that people always think about is, of course, the uniform distribution. But the problem with the uniform distribution is that if you're uniform, let's say over theta, and then you think about theta square. If you think about the transformation of probability density functions, the distribution over theta square is not uniform anymore. Then the question is, how come that you have information about theta square but not about theta? So for some reason, this transformation variance is not really nice. So you want, instead of the uniform distribution, maybe distributions that are transformation invariant. This then leads to Jeffreys priors. But again, these are then transformation invariant, but they are not necessarily uniform. So then you give more probability density to certain regions of parameter space and are not quite heavy, and allocate more probability mass to that. So that is transformation invariant, but not uniform anymore. Then of course people say, well, that's also not objective and not uninformative. And then the argument there is, okay, there are not really uninformative prior distributions, so objective Bayesianism doesn't really exist, but what we can do is all use the same prior distributions and then express our posteriors with respect to the same prior distributions. This is kind of the common thread in reference analysis. And so where you talk about reference priors, and this basically, it's like, I find this actually relatively natural because to say this is, I don't know, it's more like 200 grams or so. Of course, this is compared to a reference of 1 kilogram. So it's with respect to a reference. And so these statistical inferences in Bayesian inference based on a reference price argue then, okay, we have a reference price, we all use the same, and hence we express our uncertainty then about that. And the motivation, of course, this is what Bayesians then argue a lot, is that the whole Bayesian framework is coherent. You don't get into paradoxes as you do in frequentist statistics, but these paradoxes I'm not explaining here. So this is the prior story. So in a way, if yeah, so this is, I think, as far as priors go. Usually, in if you want to do the thing is, I think in statistical practice, priors, first of all, for most things, people don't use Bayesian inference if they still like to do frequentist statistics, so that they don't get into that. And then if you say we used uninformative prior using, for example, a Gaussian with a very wide variance or low precision, then people are also fine with it. So it's not that everybody always gets so crazy about priors then in real life. But that's briefly the prior story. Of course, there's this session on constructing priors by formal rules, which is interesting, but in the end, it ends up with what I already explained, that you say, okay, we all use similar priors, and then we just express our posterior belief with respect to that. Yeah. Other thing is that, of course, you also do Bayesian inference always. So, for example, when we next week talk about Bayesian filtering, it's not so much that we want to estimate a parameter that is fixed, but we want to estimate a parameter that changes over time, which is then called a state. And then people are not that worried about that anymore. So you still use the same Bayesian inference thing, but you use it for something that is unobservable. You might have additional parameters which you do maximum likelihood based, but then you use Bayesian inference without this big thing about, now you use a prior. If I would be fresher a little bit, I would now also give you all the things where you use priors and frequentist inference, but I don't have them in my head right now, but you do. So, yeah. Good. Any other questions? Good. Then let's take a break until 11:15 and then continue with inference summaries.